Turn over to Mark.
Okay. Thanks. I don't need a microphone or anything? No? Okay. So, I'm Mark Thom. I'm a postdoc at the UND IBM CAPSA lab, working on the AOT project Brunswick. So, largely this is going to build on, doesn't seem like the clicker is working.
I don't have to
Use a keyboard? Okay. What Ben was talking about, so if you're here for the previous talk, this is going to overlap slightly with that, at least when it comes to introducing WebAssembly. So, as most of you know by now, WebAssembly is a compilation target for programs that are intended to run in web browsers. And the intention behind that is to perhaps finally deliver on this promise that we've been hearing for 30 years about write once, run anywhere. I first heard that when I was in middle school, back when Java applets were very much hyped. That movement kind of died quietly, but now that desktop applications have largely migrated over to the web, I think that's finally going to become viable. So currently, JavaScript kind of rules the roost here, right? The problem with that is that as performance demands escalate, it's going to become increasingly difficult for JavaScript to scale to the demand. So think of like something like a virtual reality application, which is pretty numerically intensive. Like no matter how far we advance in making JavaScript run fast, it's probably not going to work, right? There's always going to be at least like an order of magnitude difference in performance involved with it. So what you really want is a compilation target that can achieve near native performance, and that also gives you some measure of security. Okay, so conceptually, this is a very simple stack-based virtual machine. At some point in your computer science education, you've probably seen Dijkstra's shunting yard algorithm, which is where you use a stack to evaluate an infix like arithmetic expression according to a set of precedence rules. So this is even simpler than that, in that it's simply things go on the stack in the order that instructions are issued, right? So instructions are followed sequentially. You have instructions to push and pop from the stack. Something like an addition operator will take two operands off the stack, add them, put the result back on. Quite simple. Usually that's contrasted with a register-based virtual machine, which involves a lot of complicated allocation schemes in order to run efficiently. So the whole idea of preferring a stack-based virtual machine in this case is to simplify the implementation end of things. So instructions are designed to be quite compact, easily transmittable. You have this very high-level S-expression representation that you probably saw from Ben's talk. This function does absolutely nothing. So all it does is it takes an integer, returns an integer. It will read the first location off of the stack, which in this case is the first parameter provided to it, pop it back off. Or rather, leave it on the stack for the next caller. So this is a no-off. There are four main data types, and those are the 32 and 64-bit integers and floats. Okay, so quite simple overall. Apart from the stack, you have heap memory in the form of the linear memory and tables. So the linear memory, in essence, is an array of arrays. How many arrays and what size those arrays are is entirely up to the implementer. Tables provide a gated form of access to things like foreign function calls or any other data that you might want to keep secure, like, say, VPN credentials. So that's kind of a really quick crash course in the specification of WebAssembly. The Ladder project, as Ben was mentioning, is essentially a set of binary tools that allow you to manipulate WASM programs. So we got a lot of use out of the first of these, which just goes from the S-expression representation at a high level to a binary representation in bytecode at a low level. The fourth is made to work with a JIT, which I'll show you shortly. That's Ben and Leonardo's project that we adapted the AOT from. You can Google it. It's on GitHub. So if you were to take a WASM program compiled to bytecode called store.wasm and run it with the interpreter with a JIT threshold of large N and a subpositive integer, what it's going to do is each function will run interpreted at first for the first n runs. Well, first n minus 1 runs, I suppose. When you get to the nth run, you JIT compile the function, and then from that point forward, you're running the compiled code. And this is a very typical modality that you find in use in JIT compilers, among them OpenJ9. Most of the code in OpenJ9 is interpreted. So the methods that are called very frequently are JIT compiled and optimized. And obviously, there's some expense involved in computing. But the reasoning is that because the methods are called often enough, the difference in performance that running JIT compiled code over interpreted code gives you will more than pay for the cost of compiling that code. So, how does this JIT work? Well, OMR farms out a lot of OpenJ9's compiler technology into a high-level API that you can use to compile programs. So the way that this you go about compiling a method, for instance, is you would subclass part of OMR's API called method builder. So within method builder, there's a number of functions that correspond to operations that you would want to issue in the compiled code. So things to read and write to memory, branch, conditionals, loops, building blocks of programming, essentially. So how do you use this? Well, as I said, you subclass the provided method builder class and just begin calling methods from the superclass. As you do that, you're building up the nodes that compose what's called the call graph of the program. So conceptually, you can conceive of a program as consisting of separate nodes that correspond to chunks of code, and those nodes are linked by edges, which correspond to transitions in the code. So you can think of this as like sequentially, you move from one block to another, just in a completely imperative fashion. Maybe you have like a switch statement or an if, in which case you're branching off in different directions depending on which branch you choose. One way to construct an interpreter that kind of aligns with this whole idea is as a direct threaded interpreter, where you have a single loop called the dispatch loop. In that you have a large switch statement, which gives you a bunch of go-tos. You process the representation of the program in bytecodes one at a time. And each case corresponds to a different bytecode, which gives you the action to perform upon encountering that bytecode. So bytecode builder is another class that OMR provides to facilitate the navigation of the call graph as it's being built. And it's just in a very nice, clean, one-to-one correspondence with what those opcodes are. So that's quite easy to approach and understand if you're just a complete rote beginner like I was months ago. When you're done constructing that object, you have a virtual method in C++. Probably you're all familiar with that, but if you're not, in C++ parlance, it follows this polymorphic object model where you can overload certain functions and call them dynamically at runtime, without the caller having to know the exact subtype of the object that it's operating on. So in this case, you override the build.il virtual method. That hooks into OMR's calls, and from there, it can take your intermediate representation that you built up using method builder and use that to produce actual compiled code. So, how does WASM AOT differ from this, and why are we doing it to begin with, which I haven't told you? Well, the whole purpose of our project is to actually explore, well, a large part of the purpose, not the only purpose, is to explore the application of some of the benefits that we've seen in AOT inside of OpenJ9 to more dynamic languages like Ruby and Python, Lua, what have you. If you were here for VJ's talk, he talked about the role of the shared class cache and speeding up startup times. The thing about that is that that takes a lot of advantage of the relatively static nature of Java as a language, right? Like you don't have like these static in advance assumptions at compile time in a more dynamic language like Python that you would have in Java. So WASM is not at all dynamic. WASM is very static. But implementing a robust, correct implementation of, say, Python and OMR that we could experiment with is much, much more complex and therefore harder to do than it is for a simple language like WASM where we've got all these pre-existing tools already. So we can move quickly. We can quickly get to a correct implementation. We can experiment with stuff much faster. It's just overall much tighter turnaround time. Oh, also, we want to adopt a lot of the OMR features to use in a more static setting. So currently, most of the work in OMR has gone into JITBuilder, which tends to presuppose that all this information that you need to compose large programs is available to you at the time that the program is running. Of course, if you're compiling ahead of time, that's not the case. So somehow you have to persist that information in between runs. So if you were to compile a WASM program into a native binary on your platform of choice, or really whatever platform supports OMR, you start with a WASM program featuring this function that I showed you earlier. So this is a module, which is like basically a bag of functions. Memory 1 specifies that you have a single array inside of a linear memory. First step is that you translate the text representation of the next expression into the bytecode. And then you feed it to the web at AOC executable, and it comes out the other side as an L-formatted object file. Now, this is only an object file. It's a completely inert thing. You can't run it just yet. In order for that to happen, you have to write a driver program. So as of right now, in OMR, there's no means to link and patch together executables using OMR. So as a workaround, we've just written this very simple driver program in C. The func not and func1 that you see actually just correspond to the functions as they occur in order within the WASM source file. So in this case, func not is going to be I32 call E, and func1 is going to be I32 ID call E. So from reading the WASM source code, we can see that the first takes no parameters and returns an int, 32-bit integer. The second takes a 32-bit integer and returns a value of the same type. And that fact is also reflected in the prototype from C functions, which actually is C++, but because we have the extern C attached, that's using C colon convention. And from there, you can just treat them as ordinary C functions. So func1 just returns its operand. Yeah, func not returns 30. That's just all the asserts are saying. Okay, so I'm just going to take you through a few changes that we had to make to OMR to make this viable. The first point of which is that WASM is designed to operate as a stack-based virtual machine. And yet, we didn't want to actually go to the trouble of maintaining a stack at runtime. Rather, we want to allocate against registers, like you would in a compiled and optimized C program. So how do we get around this problem? Well, OMR has another class that's quite useful for this sort of thing, called appropriately enough the virtual operand stack. And the only functions that we use so far are these three, which are probably familiar to you. So push and pop, obviously. Pick just goes depth elements down into the stack from the top and takes the first element. Other thing to notice is that we also pass in an IL builder pointer. So IL is a super type behind method builder, bytecode builder, as the name suggests. And the reason that you pass this in is that under certain conditions, the virtual operand stack can emit code to the compiled code. Which kind of begs the question, why would you want to do that? Well, the intention behind the design of this class is actually to synchronize state between the JIT compiler and, say, an interpreter backend. I'm not really sure if that's the right term. So if you have a stack-based interpreter that occasionally runs compiled methods, when those methods return, you want the interpreter stack to be updated accordingly, right? So that it correctly reflects whatever changes to the state that were made by the compiled code. So the virtual machine operand stack provides a commit function which actually ramifies all those changes against the interpreter stack, if you want it. That's a pretty big if, because if you don't call commits, no code will be omitted at all, which is precisely what we wanted. So here we're just using a virtual machine operand stack to maintain the state of the conceptual value stack in WASM according to where we are in the call graph. Now, the only bit of added complexity this introduces is that occasionally you have to say backtrack to a branch node and then restore the state to whatever it was at that time, but that's quite easy to do. Just a brief word about how you would actually go about synchronizing this against the interpreter state if you wanted to do that. OMR provides a class called virtual machine register, which takes information about what the structure of the stack looks like. So usually pointers to stack base, stack top, at least in the cases that I've personally seen of people using it. And I already kind of alluded to the bottom case, how you would actually synchronize. That's just by calling commit, essentially. The reason it's called virtual, again, just to ram this point home, is that none of the actual stack manipulations necessarily have to be compiled to actual code that is run. So you can use this to keep track of the state of the stack, but when it comes to actually compiling code, you're completely register-based. So we avoid all of that overhead. Another point where we ran into some trouble is with ELF file generation. I told you a moment ago that we're compiling to ELF formatted object files. For as long as I've been staring at the code, OMR supports two classes, or contains two classes, I guess I should say. The ELF relocatable file generator and the executable generator. So initially I tried to use the ELF executable generator to produce binaries without having driver programs at all, which did not work. So currently that's in a state of ongoing development. That produced a manual ELF file. We had no entry points, let alone entry code to speak of. That didn't work. So we had to go with the intermediary in the form of a driver program. So changes that were made, not yet committed to OMR at the time, they're pending on GitHub. For all I know, they might still be sitting in a pull request. Allow you to generate valid object files that are viable. So that was kind of taken care of for us. From that point onward, we had to broadcast the names of AOT functions into other methods that were being built using Method Builder in advance of them actually existing anywhere. Often not even in the runtime code cache, I can promise that. So the way you do that is by calling the define function method that Method Builder provides you, which is a bit analogous to declaring C prototypes before you call functions in C. You see this macro called function relocation. There's nothing at all special about that. This is just a non-null value that is inserted to pass an insert that occurs somewhere within the call graph, I guess you could say, of this method. So internally, OMR will take care of that for you. At least that's currently the case on x86-64. I also tried this on x390 mainframe. Support for that platform isn't quite good. So this is very much in development. Next problem came in terms of representing different WASM values on the stack. So as I told you, there are 4 primary values. If you're reading them there. These are, I'll be packing in 64-bit words. So what's the issue with that, right? I mean, in a language like C, you would just resort to something like a union. Well, the hitch to this is that in OMR, you can specify the type of the union to OMR's type dictionary class as its term. It's not quite possible to create, at least not directly, a union value within the intermediate language representation. So if we look at the virtual machine operand stack constructor, most of this is just noise as far as we're concerned. The third parameter is the type of the values that go on the stack. So because this is types, we have to go with some type. So we pick a type that's large enough to accommodate all of them, which when you compile a union type NC is all you're really doing anyway. And this is what I just told you, but if you're not familiar with unions and C syntax, looks like this. So it's like a struct, but in reality, only one of these fields is like active at any given moment in time. So by referring to these different fields of a union value in the manner that you would in structs, you're actually doing a cast between these values. Sort of. I'm kind of fudging the definition a bit, but that's essentially what's going on. So we kind of emulated that ourselves. We did what's called a bit cast, which is in fact a no-op. What I'm terming a bit cast here is actually just a transition of view. So I've got some machine word, 64 bits in length. In one instance, I'm viewing it as perhaps like a 32-bit float. The next, it's 64-bit image. Right? I just got to convince OMR to go along with that whole idea. And the way that you go about doing that is by wrapping the existing opcodes that already exist within OMR's intermediate language into some JITBuilder service, which at the time didn't exist. Leonardo ran into the same problem on WASM JIT OMR, and months ago, before we embarked on this, he actually added his own services to do this, and he probably forgot about it. So, yeah. This is fine, though. This is a good learning exercise. I mean, from what I understand, you're going to be doing something similar to this with tutorial later. Yeah. Okay, so this is fine. This actually solves the problem entirely just because due to the strong statically typed nature of WASM as a language that kind of manages all the type information for you. So I don't need to track in advance the type of an operand when it went on the stack and was cast to an I-64. The language will tell me when it's time for that value to come up. So lastly, we ran into a similar problem when implementing linear memory, and that OMR doesn't have much in the way of direct support for non-stack-based applications. So the intermediary language is quite similar to C in that most variables by default are allocated on the stack. And when the scope of a method terminates, those variables, of course, come off of the stack. When I say the stack, I'm referring to the machine stack, not the web. So how did we handle that? Well, the answer was to allocate that memory on the C side in the driver program and pass the addresses of those arrays in as pointers to the WASM compile functions. So to see what this looks like on the C side, I've got an array of values. And here are the 64-bit values. I have a WASM function that stores the second parameter to the index specified by the first parameter. And in this case, this WASM function is typed to take a 32-bit float as its only parameter, or excuse me, as its second parameter. And down here, I just have helper functions written in C to convert from float to long. And ultimately, we wound up doing something similar for so-called global variables. So allocated on the C side, the address is passed in as a pointer, of course. So. Yeah, these are directions in which we want to improve OMR to better handle these things, to better manage these abstractions. Really, it's not quite there. So just to give you an idea of how the performance of this compares to the JIT WASM, I wrote a simple program in WASM to compute the first 93 Fibonacci numbers to an array. So that's an arbitrary sounding number. Really it is, at least that's the fact that it's the greatest Fibonacci number that you can pack into a signed 64-bit integer. It's the only reason for the choice of that number. So I wrote a program to call that function 10 million times. I go to JIT, the driver program looks like this. There's 93 elements in this array. You can see from the prototype that it accepts a pointer to an array of N64s. Like I was telling you, that's linear memory. So entire run on the AOT took 2.89 seconds, which is a rather slow virtual machine I ran it on is fairly respectable, I think. JIT took 230 seconds. So what's the reason for this? Well, the WABIT interpreter that the JIT interacts with is not written for speed, it's written for ease of understanding. So there's a lot of back and forth going, a lot of like value stack in the interpreter, which is like a literal reified stack. And that ends up just thrashing tremendously. So a lot of context switches, a lot of page faults. Again, I should remind you that it's JITBuilder at the core that's generating this code. So you can get quite performant code, you just have to consider what you're doing. Okay, so what do we want to add to the WASM AOT apart from missing IL builder services that I mentioned? Well, there's actually a team trick that I mentioned was the relocation part before where I had to specify an unknown value. That doesn't work for other processor architectures to my knowledge outside of Intel. Of course, most of the development of OMR is on Intel machines, so presumably it's going to be most of the development is when it first appears, so that's kind of natural. Another thing that we want to take care of is the static relocation of constants and globals. According to information that's not immediately available to the program, but stored in, like, say, an L file or a memory map persistent cache. For instance, that's going to become pretty crucially important when we begin to AOT compile portions of Python programs. Also, we want to get rid of the need for interfacing with C of any type. You know, like OMR should be sufficient enough to generate all of these things on its own. Lastly, we want to look at supporting mixed mode compilation in WABIT AOT. That's when, as in the OpenJ9 case, you have some segment of code that's compiled to AOT, and the rest is JIT compiled, and usually you want startup code to be compiled to AOT. Just for the sake of mitigating a lengthy startup time. And in order to do that, if you want to say synchronize with the virtual machine operand stack, you're going to want to save the information that gets packed into something like a virtual machine register object, which actually tells you how to go about synchronizing. Currently, there's no support for that within OMR. Eventually, we want to start actually looking at ELF as a representation format for Python programs to see if that's viable at all. I mean, it's a research project. You know, ELF is quite a static format. Makes a lot of assumptions there. So, yeah, this is sort of a launching point for all of that. So, that's all I have. Yep, thank you.
Any questions from Mark? Okay, thank you.
Mm-hmm.